Over the course of my studies in theoretical physics, I've traveled across the continent and around the world sampling new ideas and tasting different answers to the questions of how and of why. And still, I find there remains a deep hunger which lives within me, a burning desire to share these great ideas with the people around me. And so, I have assembled a team of some of the greatest, most lucid, most creative minds I've encountered in my travels. And I call them my Titanium Physicists. You're listening to the Titanium Physicist Podcast, and I'm Ben Tippett. And now, allez, physique! In the world of classical physics, one very common, very useful concept is that of the potential barrier. Okay, so what's that? It's a strange phrase. Potential barrier. Potential is short for potential energy. Barrier is short for barrier. It's a way to describe a certain feature that some systems have, systems where your object can't move past a certain point if they don't have enough energy. So hills. Hills for kids on bikes are often potential barriers. When I was a kid, I had a bike with only one gear. So if you were climbing a hill, you couldn't change gears. So if you wanted to get over a hill, you had to get a running start. And if you weren't moving fast enough at the bottom of the hill, you'd slow down and come to a stop before you reached the top. So the hill was a potential barrier, because if you had enough energy at the start, you could make it over and cross the hill. But if you didn't, you couldn't. So, in the world of physics, potential barriers are everywhere. You know how if you throw a rock up in the air, it'll always fall back on your head, unless you throw it faster than the escape velocity of the planet you're standing on? That's a potential barrier. So what keeps two atoms from combining and having one big nucleus? It's the electric fields emitted by the positively charged protons. They push against each other, and that's a potential barrier. And what keeps two protons in the same nucleus from splitting up and pushing themselves apart to make two atoms from one? Well, there's a strong force sticking those protons together, and that's a potential barrier. What keeps the water in your dog's dish from running out on the floor? Potential barrier. They're everywhere. Okay, so, until the 20th century came around, the potential barrier was the law. The water inside the dog's bowl was stuck inside the dog's bowl. And unless a dog came along and messily drank the water and gave some water some kinetic energy to slosh over the side, the water would be stuck in the bowl forever. That's until quantum mechanics came along. Turns out, in some circumstances, quantum mechanics tells us that a particle can walk right through a potential barrier even if it doesn't have enough energy to get through. This process is called quantum tunneling, and that's the topic of today's show. So, today's guest is an artist whose work I've enjoyed for the better part of a decade. His current comic, The Non-Adventures of Wonderella, details the annoying life of a sarcastic superheroine. The writing and art are both concise, efficient, and hilarious, and you can read it and buy the books at nonadventures.com. So welcome to my show, Justin Pierce.
Hi, everybody. So,
Justin, for you today, I've assembled two very special titanium physicists, and we've got a real treat. Arise, Henry Reich!
Diddle-ding, ding, 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 ding.
Fantastic. In the world of internet physics outreach, there's only one king, with 500,000 subscribers on YouTube and 35 million views! He's the creator of the popular Minute Physics videos. Henry got his master's in multimetric gravity from the Perimeter Institute of Theoretical Physics, and he's currently employed there as the artist-in-residence, making little videos to entertain and educate you. Now arise, Tia Michelli!
Boing, boing, boing.
Awesome. Tia is a graduate student at the University of California, Davis, where she studies high-energy experimental particle physics, and she's writing her thesis on Z decays. Okay, done the intro. All right, Henry, we got to introduce wave functions. How are we going to do it?
Well, my favorite way of talking about quantum mechanics in general is to talk not in the standard way that most physicists are used to thinking about it, but using a picture called Bohmian mechanics, which is equivalent to regular quantum mechanics mathematically. It just gives you a different intuition as to what's going on. Traditionally, we're used to thinking about particles as things that move around and bump and have a very definite trajectory. They go one way and they go another way, and you always know where they are and how fast they're going. And then waves, you have waves on a string or waves on the water, and the waves, they're fluid and nebulous, and they can interfere and do other wave-like things. And it turns out that quantum mechanics, particles don't always behave like particles. They kind of are guided by these things which we call wave functions. But basically the picture that I'd like to have you think about is imagine a raindrop. And the raindrop has a speck of dust in it. So the speck of dust is our particle, and the raindrop is the wave function. And when you start off, you know where the particle is. It's somewhere in that raindrop, and it's fairly well contained. But say the raindrop falls on the ground, that water will get spread out and splash around. You could know exactly where all the water is, but that doesn't tell you where the fleck of dust is. You just know that if there's more water in one place, that's where you're more likely to find the speck of dust if you look for it. And that's roughly how quantum mechanics works. The wave function is guided by, in general, complex equations depending on the situation. But all you have to know is figure out what the wave function, which is our distribution of water, figure out what that looks like, and find the speck of dust in it. And that's where the particle is.
So is wave function just entirely random then? Or is there a rational explanation for why there'd be some segment of the raindrop that has this particle in it?
So that is an incredibly good question as to the underlying nature of quantum mechanics. At the moment, the best we know is that the particle just randomly is somewhere when you look for it. And if you do the same thing twice, it could be in different parts of the water at different times. It's kind of like running the experiment multiple times. The fleck of dust might end up somewhere else.
So the wave function is the water drop, right?
Yes, the wave function is the water drop in this picture. And the particle is basically, it's guided by the wave, is the picture. And this is very counter to what pretty much anyone who takes undergraduate physics is taught. It's a very different picture, but it's mathematically equivalent, and I find it's much more intuitive and easy to picture. You just have to say, well, we have this amount of water and the particle's somewhere in this drop. The drop gets spread out according to the Schrodinger equation, and once you know where the drop has gone, if you want to know where the particle is, if there's a lot of water somewhere, that's where you're most likely to find it, and if there's not a lot of water, you're less likely to find the particle there.
I like it.
That's a great introduction. Okay, so sometimes in physics, you end up with situations where there are some forces holding you in, but if you can make it out past a certain distance, you can escape. And these are the potential barriers I mentioned before. So, for example, there's a great one which involves nuclear forces for protons. So if you imagine an atom, it's got a nucleus, and the nucleus is made up, essentially, of a whole bunch of different protons that are stuck together. And protons have positive charge. And the thing about electric charge is the closer two positive charges get together, so if you rub your head against two balloons and you try to push them together, the closer together they get, the more of a force they feel pushing them apart, okay? So as these two nucleons, they're both positive, the closer they get together, the more of a force they feel pushing them apart. But when you get them close enough together, a nuclear force kicks in called the strong nuclear force. It kind of sticks these positive protons together.
So one analogy I heard for this is if you have like charged ping pong balls, of course, if they're the same charge, they repel. But if these ping pong balls are coated with Velcro, then when they get close enough, the Velcro sticks, just like the strong nuclear force.
Right.
So there's a threshold where it's like, if they're sort of close together, they'll repel. But then once they're actually almost touching, they'll attract each other once they get past some barrier.
Yeah.
Right. And so this threshold is the barrier. This is the potential barrier in the system. And it's spherical. So all you need to do is, in any direction, if you can take these two protons that are stuck together and move them just far enough away from each other that the electric force between the two kicks in, once you're past that threshold, they'll just move away from each other. So in this situation, essentially, these particles, they might have a little bit of kinetic energy, and what that kinetic energy will make them do is it'll make them kind of vibrate around each other. If they're stuck together, it means that they don't have enough kinetic energy to get far enough apart so that they can separate. So they just kind of jiggle around together. Classically speaking, this is kind of what's happening. And what it means in the classical picture is that they'll be stuck together forever.
So the idea is that like these two balloons that are sort of like almost touching and just sort of like hovering very close to each other, the barrier that they need to get over is something to kick them far enough apart so that they'll repel again?
Yeah. The barrier is essentially the need to get past a certain distance.
Okay.
It's equivalent to, say, having to ride over a hill with your bicycle. If you don't have enough speed, you can't make it up and over the hill. So, I've got a glass of water in front of me, and so I imagine the side of this glass of water as being the potential barrier. If the water could make it just outside this glass cylinder, it could, go wherever it wanted to. So, in the case of the nucleus, it's just like that. You have these different protons, and they're stuck inside a nucleus, jiggling back and forth. They want to get out, but they're quantum mechanical objects. And so in this Bohmian mechanics picture, we envisioned it as, in this case, imagine a cup that has some water in it, and that represents the wave function. You don't know where inside this cylinder you're going to find the nucleons, but you know based on how the water is distributed where the particle has a better chance of being and where it has a worse chance of being.
Like if it's a wine glass, there's going to be the wider part and the skinnier part, and it's probably going to be in the wider part just because there's more.
Yeah, that's
area.
right. Okay, so now we got to talk about tunneling through this thing. So we've introduced this idea of a wave function, where the wave function kind of carries around the particle. So if you had the wine glass, the chances that the particle is going to be where the column of wine is higher is larger than when the column of wine is smaller.
Right.
So the deal with quantum mechanics is that there are a few rules that govern how the wine, this liquid, can evolve. There's one simple rule in this case that always governs how this water will distribute itself, or this wine will distribute itself, which is that this volume of water can't have a sudden transition where there's water in one place and then no water right next to it. In other words, so it can't go to zero all of a sudden. In this quantum water, what you imagine is that there's water in the middle of the glass, and then there's that glass wall, the edge of the glass. But because of this rule that says that the water can't have a sudden transition to zero, it means that there has to be a little bit of water just inside the glass wall, and then inside that there can be a little less water.
So there's like these, like this glass in this example would be like have like tiny pits in the edges that were microscopic and little nooks and crannies for the water to hide as you get out to the glass edge or something. Is it like a slow gradient?
And,
that's right.
And as you go deeper into the glass, the little holes where the water's allowed to be get smaller and smaller. So you have a smaller probability of finding that dust particle within the glass.
Okay, at the very, very edges of the glass.
Yeah.
I just want to break in and point is that as nice as this explanation is, the holes actually come from the water, and the glass doesn't have the holes in it originally in the quantum mechanical picture. I'm wondering whether something we talked about it like a sponge, and a sponge has an even kind of amount of holes all the way through it, but if water only travels from one point to the sponge to the next, kind of lower and lower concentrations, if there's, a little bit of water in one part of the sponge, there'll be a little bit of it will seep out to the next side of the sponge, and a little bit of that will seep farther, and so that you get less and less water as the farther through the sponge you go.
Right. So the side of the sponge that's touching the liquid will be really wet, but then the part of the sponge that isn't directly touching the liquid will get less and less damp the farther away from the liquid you go.
So what you guys are saying is that it's the water is the thing that's pushing out. It's not a particular pitting on the container or on the wall. It's action by the wave force happens to be like water or something that's forcing this gradient to be happening.
Yeah, that's right.
Exactly.
It's fundamental to this wave function that it won't let you transition to no probability. So if it's possible, the particle can be right at the edge of the glass wall, then it's also going to be a little bit possible that the particle can be inside the glass wall, and then the deeper you go in the glass, the probability that the particle will be there decreases the farther you go. So in essence, what happens is let's say you have a glass wall that has only a finite width, like a mug that you're drinking water out of. What this means is the water will permeate the mug wall, and it will also kind of flow outside the mug. It'll use these kind of holes that it makes, and as a result, there's a little bit of water that will be outside the mug. So, because there's water inside the mug, there will also be a little bit of water inside the walls of the mug, and then there will be even less water, but it will be possible that there can be water outside the mug.
Sure.
This means if there's water outside the mug, in the description of quantum mechanics that we've been giving you, the particle itself, it's that dust particle that's living inside the water. So if there's water outside the mug, it means that there's a finite probability that the particle can be outside the mug.
Okay, that it's the part of the water that sort of worms its way through the surface of its container, that within that it can contain this particle of dust.
Yeah.
Yeah.
Because of the water's nature, this particle of dust can end up outside the mug, even though it didn't have enough energy to get over the wall.
But one of the main parts of this is just the fact that this particle on its own would not be able to surmount whatever the wall of difficulty is without this guiding it through.
That's right. It wouldn't be able to make it past the threshold if it wasn't for the nature of the water that carries it around.
If it were a classical non-quantum mechanical particle, it would be stuck there. It would never be able to escape. But it has this slight chance, because it's a quantum mechanical particle, it has a slight chance of being able to be outside of the glass.
With this, there's never going to be an outside force. Like, say that dog that, like, sticks its head in the water and pushes it over, or somebody that, like, bats one of the balloons away from the other with their hand. Is it always going to be just basically sourced on unlikely but possible way for the wave to push something through on its own? Or is there going to be some sort of outside force that sort of pushes it?
If there were an outside force, that wouldn't be quantum tunneling. That would be regular quantum mechanics.
An outside catalyst, like somebody knocks the mug over accidentally or something, that wouldn't be an example of this, right? It would have to be the water on its own seeping its way through the barrier.
Yeah.
Exactly.
Okay. I think it makes sense. I don't really know how it fits into much, because it seems like such a small probability of what would happen.
Yeah, and that's one of the big ideas is that it's such a tiny probability that it only happens very rarely. So a lot of the effects where this actually plays an important role are places where there are tons and tons of particles, and only a couple of them actually manage to tunnel through and do the interesting things.
Okay, that makes sense. I was trying to figure out the scope of this, because it seems like hitting a racquetball at a wall 1,000 times, and then, after 100,000 times, somehow it makes it through the wall or something. It seems like an almost infinite chance that it would never happen,
Tia, it's time to talk about your beer.
Okay, so before this show, I calculated how long it would take a cold can of beer to tip over by quantum tunneling. And it would take 10 to the 31 years. To put that in perspective, the universe is 10 to the 9 years old, a billion years. So it would take your can of beer sitting there, 100 million trillion years to tip over.
One with 31 zeros after this, years.
Yes.
Something like that.
So when physicists like to say that, well, anything's possible, my cat can tunnel through the wall. Well, sure, your cat can tunnel through the wall, but it might take many, many, many lifetime of the universes for that to happen.
So when a scientist tells you that something is possible, that doesn't necessarily mean that it's ever going to happen any time in your lifetime.
Or anyone you know's lifetime.
So let's get into fun examples of quantum tunneling. So there was a mystery about the sun, which was, how does the sun burn? Do you know the answer, Justin?
Yeah, some mishmash of crap in the core, right?
Yeah, it's clear fusion. There are hydrogen atoms that are mushing together and forming helium atoms. Figuring that out itself was a mystery. When they figured that out, though, they said, okay, I've described before this kind of potential well to get two protons together, right? So there's this electric force between them, and it gets stronger and stronger the closer you push them together. But if you can get them close enough together, the nuclear force will stick them together. Mm. So they calculated how much temperature that would require. So the temperature is kind of a gauge of how much energy each particle in a gas on average has. They could say, okay, if it takes so much energy for 2 protons smashing together to fuse. How much temperature would it require? And the answer is 400 million degrees Kelvin. Because of this potential barrier, 400 million degrees Kelvin. The thing is, the sun in the core is only 15 million degrees Kelvin. So you need 400, you only have 15 million degrees Kelvin.
Is that like a weird anomaly, or does it go through any sort of fluctuations like this on a normal basis?
It doesn't suddenly get 100 times hotter and then cool off again, if we're talking about that.
It's business as usual on the sun. And so they have this 100 times colder than you would need for nuclear fusion. So what's happening is tunneling. You know, it's a rare effect, but on the inside of the sun, there's lots and lots and lots of hydrogen atoms smashing together. It's really dense, and it's happening a lot because the sun is huge. So, even though it's rare, and even though these 2 protons are too cool, they're not energetic enough to smash together and meld and form a helium nucleus, they get close enough that they can tunnel into one another. So, effectively, even though it's a rare enough event, the sun has enough particles on the inside of it that this is a regular occurrence, and that's why the sun is burning.
Oh, really? So that is really the explanation for why the sun exists as it is.
Quantum tunneling.
Quantum tunneling lets it happen.
Wow.
And so one interesting side effect of this is that this is partly why it's so hard for us to make fusion happen on the Earth in a controlled way, like to generate electricity, for example, is because we don't have enough stuff here on Earth to be able to make it as dense as the sun. We can't take advantage of quantum tunneling. So we need to get a fusion reactor to be 100 times hotter than the sun in order for it to do fusion properly. So this is why fusion is hard. We have to get it much, much hotter than the sun because we don't have as much stuff as the sun does. We can't rely on quantum tunneling to help us with our fusion on Earth.
Is this reaction what kickstarts the sun originally, or is this what keeps the sun constantly going?
This is the way the sun works every day, day in and day out. The sun is mainly hydrogen and a little bit of helium, so that's how it is able to burn. Like if the sun were made of something like gasoline or wood and it was just burning, even as huge as the sun is, it would burn out in 1,000 years. So the way it can stay going so long is because it's actually only very few hydrogen atoms that are fusing together.
Okay. So it's one of those things where it's even as rare occurrence as this quantum tunneling is on something like this core of the sun. There's just so much stuff to work with there that it's happening on an ongoing basis.
Yeah, exactly. I mean, it's like if you have a 1 in a million chance, but you try it 10 trillion times,
sure,
you're pretty likely to have it happen a lot.
It's going to happen, yeah.
So Justin, there was a mystery for people when they were talking about nuclear decay. So, in essence, you start off with a heavy nucleus like uranium. Imagine a collection of uranium atoms as like popcorn kernels at the bottom of a bowl. So you had a big bowl of unpopped popcorn kernels. And then at random, they pop. So the deal is that when you pop popcorn on a stove, the rate at which they pop depends on how hot it is. But with uranium atoms and other radioactive atoms, nothing seems to matter. There's kind of a universal time scale at which things pop. You've heard of a half-life, right?
Yeah. It's the amount of time that it takes for something to decay, right?
Yeah.
50% or something.
Right. So all it says is, if you take one of these uranium kernels, the half-life's 4 years or whatever, you wait 4 years, there's a 50% chance that popcorn kernel is going to pop and turn into 2 different smaller atoms. In the 5 years after that, there is, of the 50% of popcorn kernels that didn't pop in the first 5 years, half of them will pop in the next.
So like the grannies will eventually pop as time goes on.
Yeah, as time goes on, but the deal is that essentially it's a pure statistics game whether or not this is going to pop or not. And so there was kind of a mystery as to why it was such a pure mechanism, why there was such a pure probability, regardless of how hot it was outside, regardless of how much oil you pour on the uranium atom, 50% of them will always pop within this amount of time.
I think the crux of it is that there are a whole bunch of protons and neutrons that are bound together in the nucleus of uranium, right? You could imagine if you could somehow split off some of those protons would get far enough away that the nuclear force would be really, really weak, and the electromagnetic force of repulsion from all of those other protons in the nucleus would be big enough to shoot that proton far away. So this is the barrier that we're talking about. And so there's this chance that you would quantum tunnel through this barrier, and there's a time scale that governs how likely it is that in this, X amount of years, you have a 50% chance of tunneling out. And so for each nucleus, at any point in time in the next, say, 5 years, there's a 50% chance that in the next 5 years, it'll decay, and a 50% chance that it won't decay. And if it does decay, then it's done. And if it doesn't decay, then in the next 5 years after that, there's another 50% chance, right? Because it's the same thing. You kind of start from scratch. Every instant that it hasn't decayed, you start from scratch. But because you have so many of them, because there was a 50% chance of it decaying in 5 years, in 5 years, half of them will have decayed and half of them won't.
Right. It's like flipping a coin. If there's a 50% chance, you flip it, and the ones that don't get the heads that you want, you flip it again, and you're still starting from square one.
So you keep on flipping until all the coins get heads.
Right. Okay.
So things decay. For example, uranium can decay into two smaller atoms, a thorium atom and a helium atom. And we're able to predict how often this happens. But in order for this reaction to happen, that helium atom that gets ejected from this big nucleus needs a certain amount of energy. But physicists were surprised when they measured the energy of this helium atom because they found that it was 6 times smaller than what it needed to get ejected. So the question became, how does a helium atom with such a small energy get ejected from this huge potential barrier? They used this idea of quantum tunneling to correctly predict how long it takes uranium-238 to decay into thorium and a helium nucleus. So this helium nucleus is just 2 protons and 2 neutrons. It's called an alpha particle. So you can model the potential of the uranium nucleus like this dog bowl. The nucleus is the center of the bowl, and then the sloping edges is the repulsive electric force, which would push this helium nucleus away if it could make it out there. So you can think of the uranium nucleus as having the same potential as in the middle of this dog bowl, and your alpha particles kind of rattling around in there. And it can't make it out. But with quantum tunneling, it doesn't have to go over the edge of the bowl. It can go through the bowl. And it doesn't penetrate very much. But with how much it does penetrate, it gives us the correct likelihood that the helium nucleus will make it out of the dog bowl and slide down the side and become a free nucleus all by itself, separate from the original parent uranium nucleus. So that was kind of amazing.
All right. So there's one final example of quantum tunneling that's really sexy. It's called the scanning tunneling microscope. Have you seen those pictures of like atoms lying flat on like a table? So I don't know if you know, but people can take well, they're not photographs. People can see atoms.
They can generate images of individual atoms.
Images of individual atoms. Were you aware of this?
I guess I assume that if I Google image search atoms, they're probably going to pictures of atoms, but I guess I wouldn't have known that they were actual atoms that somebody has captured in like a,
okay,
in the real world versus just like an artist's conceptual drawing or something.
Yeah. So the deal with atoms is that they're too small to see with normal light. If you wanted to see them with light, you would need a very small wavelength of light, and usually small wavelengths of light have a lot of energy, so if you tried to look at an atom, you would hit it with a photon and the atom would go flying. So in essence, microscopy is fairly limited in terms of our ability to see individual atoms. But there's this tool that people can use to see atoms, and it's called a scanning tunneling microscope.
Okay, so the scanning tunneling microscope works by you probe a surface that has the atoms on it that you want to see. You probe it with a very, very fine wire, that's whittled down to a very, very fine point that hopefully just has one atom on the end. And then you apply a voltage difference between the surface you want to image and this very pointy tip. And then you have a machine that brings this tip very close to the surface. And when you get close enough to the surface, you can have a tunneling effect between the electrons in the tip of your probe and the surface that you're probing. So when an electron makes that jump, you get current flowing. Current is just the flow of electrons. So you record this current, and that current will be proportional to the depth of the thing that you're probing, the topography of the surface that you're imaging.
Because there's going to be more electrons through the thicker parts than the thinner parts?
Yeah, so if your surface is raised and you bring your probe close to it, you'll have a higher chance of tunneling there than the places where the atoms are lower, deeper in the surface, so they won't tunnel as far.
Have you ever been to, like, you go to Toys R Us, and there's a big vertical bin that's full up of kids' balls, and they're all, like,
Sure.
sticking out. There's usually, like, nylon rubber ropes or something hanging down, and then, all the balls are kind of sticking out. So that's what the surface of anything made out of atoms looks like at close enough distance. Now, this isn't a distance we can see optically, but the deal is the scanning tunneling microscope, it's kind of like dragging a record needle near the surface. So as you drag this needle over the surface of this box full of balls, when it's close to the edge of a ball, it will tunnel better, and when it's far away from any ball, it will tunnel worse. And so you can use that to figure out where the edges are higher and where they're...
Like a depth finder or something.
Yeah, that's right.
Yeah.
And in essence, they drag the needle like microns above the surface. And then they go back and they move the thing up a little bit and then scan back across it. And they just kind of paint the surface back and forth with this needle. And then they do some computations. And they can use that to figure out how far the needle has been from the top of the surface. And from that, you can end up with pictures of atoms.
That's cool. So it works the same way that a scanner would. It just sort of passes through in several sweeps and then comes up with sort of a map based on those sweeps.
Exactly.
Yeah, exactly.
Okay. When we get pictures of atoms, it's basic. That's the process they're using. They're sweeping over the surface and making sort of like a bas relief piece of terrain on it to show the nooks and crannies, I guess.
Yeah.
Exactly.
Okay.
Any other questions?
The weird thing about this is that it's such a rare occurrence, but when you're talking about the scale of the things that you're working with, whether it's the sun or, there's such an almost infinite number of chances for it to happen that it just becomes a regular occurrence. That's the most bizarre part about this, Well,
it's like somebody has to win the lottery. It's a very small chance for you to win the lottery, but normally somebody does.
Exactly.
It depends on the circumstances. When you're like a kid riding over hills, some hills are easier to ride over than others. And the ones that are easier to ride over are the ones that will be tunneled through faster, that will be tunneled through more easily. So, mashing two hydrogen atoms together to make a helium atom, that's a lot of tunneling. So that'll be a really, really rare occurrence. So the sun can do it because there's so much hydrogen inside the sun. On the other hand, if you take a really, really radioactive, like one of these isotopes that lasts, has a half-life of like 5 minutes, so they're decaying through a tunneling process, but the chances of that tunneling event happening are really high, and so they'll all tunnel really fast. It's like playing the lottery where the odds of you winning are 1 in 6 versus 1 in 6 million.
Yeah.
So it's not always a really rare event. It really depends on the circumstances. It really depends on this potential barrier that you need to get through.
Okay.
Well, that was great. So thank you, Henry, and thank you, Tia. You've pleased me. Your efforts have borne fruit, and that fruit is sweet. Here is some fruit, some spiky fruit that's hard to get into. Henry, you get a durian.
Ow!
Oh, yeah, you use a machete or something.
No.
Tia, you get a rambutan.
Ouch! 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 Ouch!
They're not that spiky. They're just kind of spiky. Anyway, enjoy your rambutan.
Nom 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 nom.
Okay, I'd like to thank my guest, Justin Pierce. Thanks, Justin.
Thanks for having me on.
I hope you had fun. We had lots of fun. Okay. All right, everybody, my TIE fighters. Let's suppose you want to interact with the titanium physicists a little bit more. If you'd like to keep track of us, why not follow us on Twitter at Titanium Physics or join our Facebook group. If you'd like to hang out with us and socialize a little, why not join our online forum? Or, if you'd like to send me an email directly to ask a question, propose a topic, email me at barn@titaniumphysics.com. So let's suppose you want to listen to us more conveniently. If you got an iPod or an iPad, try subscribing to our show on the podcast app. While you're there, write us a review. Your reviews determine our ranking on the podcast app, which in turn determines how many new listeners will discover our show. If you have a Zune or BlackBerry, you can subscribe to our show on those doodads as well. Or you can download the Stitcher Radio app, which will let you subscribe and listen to all your favorite podcasts. You can download the Stitcher app for free onto your iPhone, Android phone, Kindle Fire, or other devices. Stitcher is convenient because it lets you subscribe to your favorite podcasts, then listen to them without working. For all this information and more, visit our website at www.titaniumphysics.com. The Titanium Physicists Podcast is a member of Brachiote Media. If you've enjoyed this show, you might also enjoy Science Sort of or the Weekly Wienersmith, so check them out. The intro music is by Ted Leo and the Pharmacists, and the end music is by John Vanderslice. Good day, my friends, and remember to keep science in your hearts.
Angela, don't be mad. There's something I gotta tell you, dear, before you come back here. I lost your bunny. I let him out of the cage. He was eating spring mix on the carpet, jumped through a window out into the haze, hop down Magnolia Boulevard, no way he'll survive.
Hey, can we do that with the lottery?
Yeah,
You wanna-
well, we do.
Can you
I
make
mean,
me
there's millions
live-
of
Can you
people
buy 10
playing.
million?
Can you
lottery
make me
tickets?
live that long so that I can win the lottery?
I think you lose money if you do that. It's like playing roulette by playing it over and over and over until you hit. You can't get money out of the lottery.
If they properly design the lottery, then that's true. That even if you bought all the tickets, you'd still the buying all the tickets would cost you more money than you would get from winning. But people and economists, I believe, I don't remember where this was. Somewhere, maybe it was in North Carolina. Something. So at some point in the last 10 or 20 years, some economists figured out that a lottery in some state that was worth like $15 million or something was actually, the lottery prize was actually bigger than the cost of buying all the tickets. So they got a bunch of investors together and they bought all of the tickets. And then they had some snafus along the way. They're actually buy millions of lottery tickets, but they managed to buy all the tickets for like a $7 or $8 million, and then they made $50 million off of it, guaranteed, basically. So that was a poor design on the part of whoever designed the lottery.
Yeah.
I don't think most lotteries are like that.
How did that work? It was like there was like a buy 10 get one free deal or something. Was that it?
I don't remember. There was something weird that allowed them to do that.
Yeah.
So with that in mind, from what I've heard, half-lives seem to be pretty on the money. Like you can say like this has a half-life of 2 years or something like that. Is that always going to be a constant, considering the fact that like quantum tunneling is such a rare occurrence and almost random in its nature?
Well, if you think about the number of atoms in, something like a kilogram of uranium, you can imagine doing this, with coins. And if you do it with, 10 coins, yeah, you're going to have fluctuations in terms of how big you actually measure the half-life to be. But when you do it with a trillion coins, all of that's going to get smoothed out just by the large numbers.
Yeah, so even though it's sort of random in nature, seemingly, as you back out more and more, you get sort of almost an even constant, even though within that constant there's so much irregularity.
If you waited long enough that there were only a handful of the atoms left, then you might actually say that you wouldn't really be able to define a half-life anymore in the same way, because you would start to see the probabilistic effects. But yeah, it's like if you flip 1 million coins, you're going to get pretty close to half of them being heads and half of them being tails. If you flip one coin, you're definitely not going to get half of them heads and half of them tails. It's either going to be heads or it's going to be tails.
Right.
So.
Yeah. I helped make these pictures when I was an undergrad. I followed around this so much wiser grad student, and he was working on one of these. He had this giant, it looked like a small submarine. It was a vacuum chamber. And inside, there was so little there was less there than there is in outer space. And so inside here, he had his surface that he was scanning, and he had this little tip, and I actually got to help him make those little tips. You blow little bubbles of acid, then you dip this wire into the bubble, and it makes this very fine point.
So it's tapered and sharp that it's like, it basically is, the tip is about the size of an atom?
Yeah, the good ones are.
Yeah.
The bad tips we have to throw away are, yeah, there's a lot of those ones too.
How do you know when you're like, okay, this is good enough? Like when you're talking about something that's like, 1/10000000th of a millimeter or something.
So these guys, these other physicists on the show are theorists. I'm an experimentalist. The way I know it's good enough is I try to take data with it. And if the data's no good, then I use a different tip.
Let's talk about wires first because it's so stupid. And then
I like it.
And then we'll talk about scanning tunneling microscopes, okay? Alright.
I know nothing about this, so I'm excited to hear it as well.
Okay, so the following facts, I'm not willing to put my life savings down on being true. I heard about this as an undergraduate, and on the internet today, I confirmed it on the internet from another undergraduate textbook. But that's the only place I've heard of it happening. But apparently, okay, so copper, it's what you make your wires out of. Let's say you want to splice 2 copper wires together, Justin. What do you do?
I suppose you'd fray the edges of the wire,
Yep.
and then you would sort of turn them into each other and then tape it up again or something.
Yeah, you twist them together, right?
Yeah.
So the idea here is copper's a good conductor. You press 2 copper pieces together, and then the electrons will flow from one to the other. Okay. Here's the thing. As soon as you strip the copper, it stops being shiny immediately. Essentially, copper oxide forms on the outside of it. And copper oxide is a really good resistor. It's a bad conductor. Electrons don't flow through it very easily. Okay. So electrons move through copper like a fish through water, but not so much through this oxide. And so when you twist these 2 copper leads together, you're essentially making a sandwich. And you've got copper as the bread, and then this bad conductor in between. So, apparently the deal is that electrons can, if you want to pass a signal through those, if you want to shoot electrons down one copper wire and have them come out the other, sometimes they tunnel through that barrier. So, the moral of the story is, even though tunneling is a crazy quantum phenomenon, sometimes you can still see them on kind of household levels. It doesn't just happen inside the sun and inside Godzilla.
Did the textbook tell you how much of an effect this actually is? Like how much it affects, like how much resistance there is, or how much the tunneling reduces the resistance there would otherwise be?
I think there was something like I don't know. I think it threw out there was like a 10 electron volt barrier or something like that. So unless you had 10 volts or something going through the wire, classically you shouldn't be able to get a current through it. But what happens is, at lower voltages, like 7 volts or something, you can still get current passing through the wire. It just has to tunnel through this connection. And so you can still get a signal through the wire, even though, you've made a pretty crappy connection.
That's super cool.
So
I
like
connect crappy wires all the time in the lab.
I know. I had no idea it was so crappy.
right.
If,
So
if it's actually true, I'm amazed.
So it's like the second that a copper wire gets exposed to air, it gets oxidized to the point that it's kind of useless, and it's completely depending on this quantum tunneling just to function.
Well,
is the argument?
Kind of. So we've been talking about potential barriers, like a kid riding over a hill with his bike. So if you put enough voltage through the wire, it's like a kid on a motorbike or a rocket bike. It doesn't matter what the hill is. It can go, zoop over the hills. So if you put enough voltage through the wire, it doesn't matter that the connection's crappy. It's kind of like how if you take high enough voltage, you can get like an arc through something. I mean,
Right.
at a high enough voltage, anything will break down. But at lower voltages than should be classically possible, you can still get electrons passing through. It's just that they tunnel through. So it's not entirely useless. I think at normal operating voltages, things usually pass through. But maybe on the level of electronics, like wristwatches or something, it wouldn't work except for tunneling.
Wow.
Well, I have another example of a barrier, which is kind of maybe can be a transition into tunneling. I think we're probably all familiar with when you're underwater or you're looking at a fish tank, sometimes there's that point where instead of seeing through the glass or through the surface of the water, you'll see a reflection of everything else on the other side. And this is called total internal reflection. And what it means is that if you get close enough to one of the sides of glass on a fish tank, the light, when it hits that glass, it all bounces back to you, and you don't see anything from the other side. So the interesting thing is that, of course, light is an electromagnetic wave, and so this electromagnetic wave doesn't just stop instantly when it hits the edge of the glass and reflects to you. It actually falls off a little bit, it decays, the wave kind of waves until it gets to the glass, and it bounces off, but it waves a little bit into the glass as well, and that falls off.
Evanescent waves.
Yes, exactly. It falls off very quickly, like an exponential. And so that's a situation where there's a barrier that glass is thick enough that the wave can't get through it. But what it turns out, if you actually make the glass thin enough and have, say, more water on the other side, then in a situation where the light would have reflected off of the glass initially, if you add water on the other side and make the glass thin enough, that little bit of the electromagnetic field that was falling off and decaying by the time it gets to the other side of the glass, it hasn't decayed enough to not do anything, so it actually continues on that side as well. And you get, the light will also go through that side. It's called frustrated total internal reflection. The reflection doesn't actually happen as much as it would otherwise, because some of the light can get through, and it does, in many ways, just tunnels through the glass.